Hello guys, welcome back. In the last video we looked at, let's go back here, we looked at this simple neural network with one hidden layer and the two inputs and an output layer. So in this network we used the rectified linear unit as the activation function. And we discussed that activation functions actually help you define the nonlinearity in the model. So why we chose rectified linear unit, this is something we will look into today. And the topic of today is actually activation functions. So as usual, I will quickly take you through the ML cheat sheet. And here you can see that we have a couple of activation functions. You have the linear ReLU, which is a version of a linear unit, and you have rectified linear unit. You have leaky ReLU, which we'll look into too. Have the sigmoid and tangent function and the softmax. So quickly through them, this is how the linear looks, and it's a straight function, quite easy. And the exponential linear unit is widely known as GELU, of course, and you can see here it actually has, it's not zero as defined before, but you have this that makes you don't get the dying problem, the dying convergence problem. So you don't, the gradient doesn't die when the values are negative, basically. And then you have the rectified linear unit, which we already used, which this one just takes the maximum of zero and the output of the neuron. So zero, and you remember we discussed this, and the problem here is that you actually lose a lot of, if the number, there are a lot of negative numbers, you get the dying gradient problem. So you lose all these numbers. And then we have Leaky ReLU, which actually gives, in this you just add an alpha, which is quite small, usually 0.01, and you will get this. So you adjust and give it a little bit of a slope, but it's not zero, at least for now. So you save the gradient from dying. Sigmoid, the classic S curve. So in this one, you have quickly values between 0 and 1, and if it's zero, you get about 0.5. It's not guaranteed that you get zero point 0.5 every time. So we'll look into this also. And this Tanh just squashes everything between 0 and 1, minus 1 and 1. And we'll look at this too. And lastly, Softmax, which gives you probability distributions. So this is a quick overview. So let's just look at them actually in the notebook that I've created. So I know if math is not your thing, don't even hassle it, because the sigmoid function, what it does is it actually takes the values and squashes them into a range between 0 and 1. So the formula is quite easy. It's this means activation, and then you have 1 divided by 1 plus the exponential of the output you had in the neuron. So negative, of course. And this is how it looks. It's S-shaped. I've just done a quick implementation of this so that in the notebook, so that you can see the values. So if you don't want to do the math, think of it like this. If the value is a big negative number, you go towards 0. If the value is a huge positive number, it goes towards 1. And this also comes with a problem, of course. So if it's so close to 1 that the convergence slows down convergence when the numbers are very big. And as you can see here, about 0.5 for x is equals to 0. So this is the sigmoid activation function, and you will get 0 or 1 usually, and it's kind of mostly used in the output layer. So if you flip a coin and you want to know if it's heads and tails, then you will most probably use this function, and it's mostly used in binary classification. And then you have this one I would not go deeper into, but it's the hyperbolic tangent, which looks like this. Kind of resembles the sigmoid function, but it also has the values between minus 1 and 1. This is cool because it gives us 0 as the center. So as you can see here, this zero-centered nature leads to faster convergence, but we also have the similar problem of the gradient vanishing in the vanishing gradient. And this we'll look into this quickly here. you can see it's zero centered. This is the pros, and still suffers from the vanishing gradient problem. And although it's less severe than the logistic sigmoid. And let's look at the rectified linear unit. Quite easy. F of x is maximum of 0 and x is the output from the neuron. As you can see, this is really good, but again, we have the dying gradient problem, or the dying gradient problem. To fix this, we can introduce an alpha, and this alpha is supposed to solve the dying rectified linear unit problem. So there's the negative values in here. See, the negative values actually start getting a slope, which you will see here. I called it keep alive value, which keeps the gradient alive. So if we get a huge negative number, the gradient is still alive, but with a very small, very small slope. So that solves part of the problem. And that's one variant of the rectified linear unit function that solves one problem. So there are different functions, which different versions of this. You have the Gaussian error linear unit, which can solve this problem in another way, and then you have the ELU, which is the exponential linear unit. And as you can see here, you change the x with an exponential -1, and you still have the alpha. So that's about the linear the linear functions. And let's look at lastly at the softmax. So softmax is good because it helps you when you actually use it when you have a lot of probabilities. So let's say you have 10 different classes. You have you let for example, you have 10 pictures and you want to remember those pictures. So let's say it's 1, 2, 3, 4, 5, 6. You take a picture and you want the model to predict that it's 1 or it's 5. This is where you would use softmax activation function because it outputs a probability distribution and it considers all inputs. And as you can see here, we will get the class with the highest input. So you will see the sum of probabilities and then you will see the outputs here. And if the highest probability wins. So if you look at this here, this is also in the note implemented in the notebook, and you can check out this notebook later. So the function is that you take all the exponential of the output and you sum all the outputs up to the last output and find the exponential of that too. So that's how you do the softmax function. We will look into this later on when we do multi-class classification. But as for now, let's focus on the rectified linear unit and the sigmoid, which gives us 0 or 1 usually. So without making it really difficult, let's go back to our easy neural network, the one we had in the last video. We have the weights, we have the biases, and we have the ReLU function. And here I've quickly defined the sigmoid function. Let's see. Sigmoid. Come on, sigmoid. And then we have so here we are predicting with rectified linear units. So I will do the same, but now I'll predict with the sigmoid. And let's see. Once we've done that, we have y hat. That's good. Return y hat. Good. Just to make it why not. And let me just add another loss so that we can actually go through the weights and the biases for everything and print the same values for both. So this is why not for sigmoid. Sigmoid, yes. And now we predict for ReLU and do the values for ReLU there, and we do the same for predict with sigmoid. And let's add one more for the loss. I see I have an error there, but see the loss with sigmoid. Sigmoid, and this one is actually changed to ReLU. So let's see the difference, because we know that the rectified linear unit gets 0 or 1, and it gets 0 for the negative values, and the values above the positive values keep their own values. But for this sigmoid, we actually squash the numbers between 0 and 1. So let's run all. How far have we come? Oh, we have to connect. And guys, just use Google Colab. There's an error here. Let's see. Predict network with ReLU. Their math is not defined. So I have an issue here. X1, X2. Okay, I will do the error. This is something you also have to do a lot. And I found my error there. And I will restart session and run all. Let's see if we get to run everything here. What is the issue now? Predict name math is not defined. Oh, math. Oh, this is where it is. Import math. Oh, wow. I forgot to import that. And guys, if you are using Google Colab, it will help you to actually write the code. So I will not need that now. So let me restart session and run all. Another error. Predict with network is not defined. Predict with network ReLU. Yes, perfect. And let's do the same for the other one. Predict with... Oh, predict with network Sigmoid. Yes, I will be running it all and just finding the errors and fixing them on the go with you. Okay. Predict with network Sigmoid is not defined. Oh, that's it again. Perfect. So now this should run. Let's go. See, another error. Yes, one more error. MSC loss, why not is not defined. We defined why not here. So, okay, so, oh, of course, small errors everywhere. Why not? So let's quickly do this. Perfect. Now you've joined me in a little bit of looking for the small errors in our code. Everything run, and as we can see here, the sigmoid had a huge loss, and the MSC loss value was quite small, as expected. And when we predicted it with sigmoid, we got 1.0, and this is because sigmoid actually isn't supposed to be used in this case. And this is something I wanted to show you too. You need to understand when to use these different activation functions. So sigmoid is usually used in the last layer and the output layer, and ReLU is mostly used in the hidden layers to, as you could see here. So with the outputs here, you could see that ReLU gave us a small loss and almost 8 because it's 4 plus 4. And here that this was totally off. So learn when to use the different functions, learn the math and how they actually are supposed to work. So if it's binary classification, sigmoid, let's go back to sigmoid. Sigmoid gives you, or the hyperbolic tangent, sigmoid gives you 0 or 1 binary. And if you want more multi-class classifications, use the Softmax, because it actually gives you all the probabilities for the different classes. So here is a table on the summary of all the activation functions. And if you're interested in this, I will drop the link to this down here, and you can read about it. And next, we would actually implement a neural network from scratch. And the neural network will actually be predicting taxi prices in New York City. So stay tuned and we will create this model together. See you next time.